All right, for practice number 1, we got a baseball being hit 4 feet above the ground, initial speed 120 feet per second, angle of 23. So I'll start off by just writing the equations. So x is going to be 120 cosine 23 t. Y is going to be negative 16 t squared plus 120 sine 23 t plus 4 feet off the ground when it was hit. And what we want to know is, will this clear something that is 300 feet away? So I'm going to set x equal to 300 and solve for t. So when I do that, I will get t equals 300 over 120 cosine 23, which is approximately 2.72 seconds. I'm going to store that in my fancy calculator, and then I will plug that into the y equation to see what it is at this time, and I got 13.32 feet. Now, it asks us whether it clears a fence that is 15 feet tall. So the answer is no. It will not clear because 13 feet is under 15, so it's going to hit the wall. Too bad, no home run. Now, the second part of this assumes that there is a wind gust that is blowing horizontally in the face. So that means it's going to slow it down. So we actually know the answer is going to be no already because it was no without changing anything. And now we're about to slow this thing down by doing a minus 10 because it's slowing this down, which is just going to modify this equation in a lot of places. Down here, this will just be a minus 10 now, which means this isn't going to be 2.7, but 2.99. So when I plug 2.99 in, I will get a height of 1.34 feet. So our answer is still no. Now, if this had been a wind gust coming from behind and actually helped him, and that was a plus, my guess is that this probably would have cleared the fence then. But unfortunately, that's not the way the problem was written. Practice number 2, bottom of the 9th. Cubs are behind, 6-3, bases are loaded. Sammy Sosa, up at bat. Swings, makes contact with the ball 3 feet above the plate. Angle 20 degrees from the horizon. Velocity of 150. Hit it straight towards center field where there's a fence 400 feet away from him, 20 feet high. Will he make this grand slam and win the game for the Cubs? Let's find out. Start off by writing his equations. 150 cosine 20 times t. Y is going to be negative 16 t squared plus 150 sine 20 t plus 3. We want to know whether or not it's going to clear something that is 400 feet away, 20 feet tall. So I'm just going to set the x equation equal to 400 and solve for t. That's going to be 400 over 150 cosine 20, which is approximately 2.837. Plug that into the y equation to see what's going on with that and how tall it is. And when we do that, we get 19.73 feet, which is under 20, which means no, he did not score a grand slam. But hopefully they got a couple of runs in, and hopefully it wasn't the last at bat. I don't know anything about baseball. I'm pretty terrible at most sports, actually. So, for question 3, we have a baseball hit towards a 15-foot high fence that is 400 feet away from home plate. Ball is hit 2.5 feet above the ground, leaves the bat at an angle of 30 degrees. We want to find the initial velocity needed for the ball to clear the fence. So this is kind of tricky. Let's start off by just writing what we know about this. So x, we don't know the velocity, but we do know the angle. We don't know time either. Y, we have negative 16t squared, still don't know that velocity. And we know that it was 2.5 feet above the ground. So what I'm going to do is use that information that they gave us, which is the 400 feet away and 15 feet high. I'm going to start off by setting the x equation equal to 400, and I'm going to solve for v. So when I solve for v, that's going to be 400 divided by this cosine 30 times t. Okay, so that's what this v value is. And what I can do is substitute that in to the y equation, because the y equation has 3 unknowns right now, y, t, and v. By substituting this in, we now will only have y's and t's, and we happen to know that we need to clear the fence, which is 15 feet tall. So we actually have just t values in here. So if I rewrite this, 16t squared plus this 400 divided by cosine 30t times sine 30t plus 2.5 has to equal 15. So let's take a look right here. These t values are going to cancel, and sine over cosine is actually just tangent. So I have negative 16t squared plus 400 tangent 30. Remember the t's canceled, plus 2.5 equals 15. So I only have one unknown right here, t, so I'm going to subtract 2.5, subtract 400 tan 30, and ultimately divide by this negative 16. So when I do all of that crazy stuff, I'll get t squared is 13.65, which means that t is going to be about 3.69, and I'm going to store this. The reason I'm storing this is because I'm going to take it and plug it into this velocity equation and figure out what is the velocity when t equals 3.69. So I do cosine 30, very carefully, plug this into the calculator, and I will get 125.00. So what that says is that we need at least an initial velocity of 125 feet in order to clear feet per second. Should include that units, it's important. We need at least 125 feet per second in order for this thing to clear that fence. Anything less, and then this will not work out too well for us. For practice 4, we have similar to what the first example was for this day. We have two people standing 50 feet apart from each other, facing each other, throwing things at one another. So we're going to start off with Xander. His equation is going to be 35 cosine 40t and negative 16t squared plus 35 sine 40t plus 3. Next, I will have Nick. So he's going to start 50 feet away from Xander, so we're allowing Xander to start at 0, 0. Nick is going to start 50 feet away, and he's throwing it in the negative x direction, so 30 cosine 45t, and the y equation will be negative 16t squared plus 30 sine 45t plus 4 for his initial height. Want to figure out whose ball hits the ground first, so we're going to let y equal 0 and use our quadratic formula. So remember that we always just write down a, b, and c, and you also write down what the quadratic formula is. This is all part of your way of showing me work. I get negative 0.12 and 1.52 seconds, okay? And I'm going to use the stored value that's here. So before I actually do anything with Nick's equation, I'm going to keep answering Xander's. So we want to know how far did it travel in the horizontal direction. So I'm just going to take that 1.52, evaluate the x equation at it. I get 40.988 feet. I will continue along here. Part D wants to find the maximum height, so I'm going to do negative b over 2a. And since I already have those stored in the calculator, I can just literally write negative b over 2a. I'm going to get 0.703. And I'm going to plug that into the y equation, and I will get 10.908. So now that I've kind of finished up all of that stuff with Xander, we can jump back over to Nicholas. Want to figure out what his max height is. So again, y equals 0. I have to write down what a, b, and c are. I'm not going to bother rewriting the quadratic formula, though. So there we go, 4. And I'm going to get that t could either equal negative 0.16 or 1.49 seconds. Okay, so I want to know whose ball hit the ground first, so it's going to be Nick again. And I'm going to take that stored value, and again, I don't care about this 50 part or the fact that he's throwing it negative. I just want to know how far he threw it, so I'm doing a modified x equation here, where I'm just plugging it into the 30 cosine 45 times t at 1.49, and when I do that, I will get 31.67 feet. So that means that Xander threw the ball further. For seeing the max height here, again, t equals negative b over 2a. Let's plug that in, I get 0.663. Evaluate the y equation at that, and I get 11.03 feet. So that means that Nick's ball went higher. So hit the ground first, but went higher. This one went further, but not quite as high. For the last part for this one, I'm just going to set the x values equal to each other. So 35 cosine 40t equals 50 minus 30 cosine 45t. I will add this to the other side, factor out that t. I'm just going to do it all in one giant step, and then divide. So I end up with something like this, which gives me approximately 1.04. I'm going to plug that in for each one of them. So Xander, when I plug it into his y equation, I'm going to get 9.79. And then for Nick's equation, 1.04, I'll get 8.74. So these are most likely not going to collide. What we could do is subtract them to figure out what this is. It's 0.337 of a foot. If I multiply that by 12 inches, I'm going to get that it's approximately 4 inches apart. And that is most likely going to be perfectly fine for them to not collide. But we do have some things that we could think about, like if you have one ball here and it has a radius of like 2 inches and someone else throws another ball and its radius is also 2 inches, then these things probably would actually hit right there in the middle because their distance that we're calculating is from the center of the ball. But we're not really thinking about that too much. That's a little extra. For practice number 5, we have Esme and Marissa. I have spelled Esme's name wrong in the answer key. My bad. That's what happens when you go too fast, not paying attention to things. So I will start off by writing her equations. Okay, so for Esme, that's going to be x equals 33 cosine 25t, and y equal negative 16t squared plus 33 sine 25t plus 5. For Marissa's equations, going to Marissa. Okay, we got x equals, she's starting 100 feet away from Esme and is throwing backwards, so I'm going to subtract. And we have the y equation, negative 16t squared plus 37 sine 36t plus 4. So first part of this says, will Esme's Frisbee reach Marissa? So what I need to do is figure out at what time this hits the ground and then figure out what the x value is there. So I'm going to do y equals 0 and do my quadratic formula. So doing this in the calculator, you get, let's see, we don't care what the other number is. So I just take that one right there. That's in seconds. I'm going to store that, but just plug it immediately in to the x equation. I'm going to get 34.23. So the answer is no. This is not going to actually make it to Marissa. Marissa's at 100 and Esme's Frisbee hit the ground at 34 feet. Too bad, Esme. Let's see if Marissa had better luck. Same exact idea. We want to know, does Marissa's Frisbee reach Esme? So I'm going to do y equals 0 using Marissa's equations now. So a equals negative 16, b is going to equal 37 sine 36, and c is going to equal 4. And doing the quadratic formula, blah, 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 I'm going to get 1.52, which I store. And I'm going to plug this into the x equation, and I'm not actually going to modify like we have been. I'm going to plug it into this exact one because I want to see if this x equation actually equals 0, then that's where Esme is. So I'm going to do that, and I get 54.4. So no, Marissa's Frisbee didn't reach Esme because Esme is chilling at x equals 0, and this Frisbee landed at 54.4. Last but not least, we want to know, will their Frisbees happen to collide? I think we actually could figure out that this isn't going to work out based on the numbers that we've already done and where they've landed, but that's okay. Let's just go through the motions here. So I'm going to set the x equations equal to each other, just like we've been doing, and then I will try to get all the t values on one side by adding this to the other side, and then I will factor t out all in one step. Hopefully that's not too much for you to figure out. So doing all that gives me approximately 1.67. I'm again going to store that. I'm going to plug it into Esme's y equation, and I'm going to get negative 16.37. That's pretty impossible in real life to have a negative y value. And when I plug it into Marissa's, I get negative 4.32. So there's definitely no danger of these things colliding because they are nowhere close to each other. They've hit the ground before their x values are equal in the model. Last one here, we have to find the minimum distance between Esme and Marissa's frisbees. So I'm going to switch myself back into function mode. I'm going to jump up to the y equals, and I'm just going to modify the equation so that they match what Esme and Marissa's equations are. So you can do this by either just retyping them or very carefully editing what the numbers are to make them line up. So here I have Esme's in. Now we'll do Marissa's. There we go for that one. Let's just edit this one, make that a 7, make this a 36, and make that last one a 4. Okay, now you'll notice that it actually re-highlighted all of these, so I need to go hit enter on all of them so that it only graphs the minimum value one. And let's just hit graph and see what happens. Well, I don't see anything, and that's because I could cheat on my answer key and see that it is higher than I thought it was going to be. So I'm going to set the y value to 0 and this to 20, and we'll just hit graph again. I should see something. There we go. Just hit second calc, going to do minimum, and I'll remind you that your calculators probably graphed that extremely slowly. It is a very complicated equation for it to do. I'm just going to make sure that I move myself past it on either side before I hit enter. Remember that x is really t, so this is 1.64 is time, and then 11.93 would be the minimum distance, except that we know that Esme's hit the ground at 1.14, and Marissa's hit the ground at 1.52, and this says that their x values are equal at 1.64, but they've both been on the ground already. So all I need to do to figure out how far apart their minimum distance is just figure out how far apart they are when they hit the ground. So Esme's landed at 34, Marissa's landed at 54. If I subtract them, I get 20 feet. So that will be the minimum distance.